Welcome back to the Deep Dive, where we take the fire hose of technical information and distill it down to the essential, fascinating insights you need to know. Today, we are taking a deep, calculated look at the future of flight advanced air mobility and the engineering compromise that, well, it just has to happen to make eVTOLs a commercial reality.
It's the ultimate reality check. I mean, physics imposes these rules you just can't ignore. For years, the dream was pure electric flight, right?
Of course, clean, quiet, simple.
But when you look at the fundamental numbers, you realize the magnitude of the problem. It's what we call the energy density gap. Current, commercially viable lithium-ion batteries. They're hitting a ceiling around 200, maybe 250 watt-hours per kilogram.
And what's the gold standard we're chasing? Where do we need to be?
Well, the standard is traditional jet fuel. Jet A1 packs a staggering 12,000 watt-hours per kilogram.
Wow.
So we are facing nearly 2 orders of magnitude difference in raw energy storage capacity. You simply cannot engineer your way around that gap with today's tech.
That disparity is just enormous. And as you said, it's the root cause of what the industry calls range anxiety. A pure electric eVTOL becomes an extremely limited tool. It's great for short sprints, sure, but it can't deliver the robust endurance, the payload, the reserve requirements.
All the things you need for reliable, certified urban and regional transport.
Exactly. And that is precisely why, from a strategic engineering perspective, the P13 series parallel hybrid system has emerged.
And this isn't just a temporary fix, a stopgap.
No, not at all. It's the necessary strategic bridge. It's specifically designed to combine the tremendous energy density of fuel, that's for your endurance, with the high responsiveness and torque density of electric power.
Which you absolutely need for those critical vertical flight phases.
Takeoff and landing. That's where you need instant power authority, and that's where electric motors shine.
Okay, let's unpack this mission then. We are going deep into the brain of this hybrid vehicle. We are essentially defining the engineering specification for the Energy Management System, or EMS.
And you should think of it less like a simple flight controller, more like the central nervous system. It's the intelligent core that has to mediate this fundamental three-way trade-off.
It's a constant balancing act.
Maximizing flight performance, ensuring absolute non-negotiable safety for airworthiness certification, and maintaining the low operating cost you need for it to be commercially viable. It has to be flexible, but it also has to be perfectly certifiable.
That's the mission right there, providing the detailed spec for this smart brain. As propulsion architects, we're dealing with the most complex part of the system. It's the control layer. It has to synthesize inputs from the battery, the engine, the transmission, the pilot.
All in real time.
All in a real-time high-speed loop.
Yeah.
This isn't just about managing components. It's about managing the fundamental physics of the vehicle's capabilities second by second.
So to appreciate the complexity of this EMS, we first need to appreciate the complexity of the beast it controls, which is the P13 architecture itself. It's an intentionally flexible topography, right? It gives operators options. But that flexibility means the EMS is facing a massive, high-dimensional control headache.
That's a good way to put it. A headache. We deliberately engineered the P13 topography for maximum operational scope. This system is structured using what we call a MECE approach.
Mutually exclusive, collectively exhaustive.
Exactly. It helps us break this highly coupled system down into 3 distinct domains that the EMS has to constantly manage.
Okay, let's start with the parts that actually make the vehicle move, the actuators.
So we have 3 distinct torque actuation points that the EMS must dynamically control and blend. First, you have the internal combustion engine, the ICE. This is your long-distance runner. It provides the high energy density for range. It's coupled to the driveline, but, and this is key, its torque response is relatively slow.
Right, there's a lag. And the electric components that interact with that ICE.
The second point is the P1 Integrated Starter Generator, or ISG. This unit is coupled directly to the ICE's crankshaft. It's absolutely critical because it performs 3 very different roles.
Okay.
It starts the engine. It can act as a motor to add torque to the ICE's output, kind of like a mild hybrid car. Or, most importantly, it can act as a powerful generator to create electricity from the ICE's mechanical power, feeding either the battery or the main propulsion motors.
And that's the P1 and P13. So what's the final piece of the propulsion puzzle?
That's the P3 propulsion motor. This is the independent drive unit, usually coupled downstream to the main rotor or propeller shaft. P3 is your primary means of delivering instant, precise, high-frequency torque.
Which is absolutely critical for attitude control during hover and those vertical phases.
Exactly. So that's 3 dynamic power injection points.
Okay, that covers the force application. What about the source of that force?
That's the second domain. The two energy sources that must be continuously balanced. You've got aviation fuel, the high-density source for sustained endurance, and then you have the high-voltage battery energy storage system, the ESS.
And the ESS provides that instant, high-rate power for transients. But it's the fragile resource. It's the one the EMS has to protect.
It's the expensive, life-limited asset. That's the key.
And finally, the element that actually makes this a series parallel hybrid, which is what differentiates it from, say, simple hybrid cars.
That is the one key decoupling element. The K0 clutch. Think of the K0 clutch as the transmission's lockup mechanism. It's the gatekeeper that determines the entire system topology in real time.
Okay, so if K0 is closed.
If K0 is closed, the ICE is mechanically linked to the driveline. It can drive the propulsion system directly. We call that parallel mode.
And if it's open.
If K0 is open, the ICE is decoupled. That means the vehicle could be running purely on electric power. Or the ICE can run independently, just driving P1 to act as a generator and charge the battery. That's series mode. The EMS controls all of this in milliseconds.
So if you're the EMS, you are constantly juggling 3 actuation points, 2 energy sources, and deciding the state of this decoupling clutch. You're not just managing components, you're solving a complex equation with 6 variables that change constantly.
Precisely. This creates what we call a high-dimensional, multivariable, and multi-objective optimization problem. It requires the EMS to instantaneously allocate power among the ICE, P1, and P3 while simultaneously balancing 2 deeply conflicting goals.
And what are those conflicting goals?
First, the immediate objective, minimum fuel consumption. That's for mission efficiency and cost. Second, the long-term strategic objective, maximizing battery life, specifically managing its state of health, or SOH.
Right, because using the battery aggressively saves fuel today.
But it rapidly degrades the battery's SOH over thousands of flight cycles, and that turns a cheap flight today into a multi-million-dollar battery replacement cost tomorrow.
So the EMS isn't just a flight controller, it's an asset manager. It has to decide, every single second, whether to burn expensive fuel now or degrade an even more expensive battery pack now, knowing that choice has massive downstream commercial implications.
That is the core conflict. And the EMS has to make that economic trade-off thousands of times every flight. And to make matters worse, the load environment for an eVTOL is far more, well, violent than an airliner or even a car. We have a highly dynamic load context.
Let's discuss those extremes. What kind of power fluctuations are we talking about?
Okay, start with vertical takeoff and climb. This is where the physics demands peak power. We are talking about power requirements often 3 to 4 times greater than what you need for sustained cruising.
And the battery's taking a huge hit there.
A huge hit. If the battery is providing a large share of this power, it's being pushed to extremely aggressive discharge rates, often exceeding what we call 6C, and sometimes pushing peak pulse discharge limits up towards 10C. The system must deliver perfect synchronization and maximum power under intense electrical and thermal stress.
And then you transition to forward flight.
You enter cruise. The power requirement drops to a baseline level. Now, efficiency is paramount. This is the phase that defines your useful range and the commercial viability of the flight. The EMS shifts its entire focus from pure power delivery to maximizing fuel economy.
And the most safety-critical phase, landing.
The landing approach and the final vertical maneuver require another high-power spike. You need that for precise control and maneuverability. But here's the danger. After a long cruise, the battery's state of charge, the SOC, may naturally be low. So the EMS must preemptively guarantee a robust state of power. The SOP is available. That's the ability to deliver that high current instantly, even when the energy storage is nearly depleted. You simply cannot lose control authority during landing because you've run out of power.
So the EMS's ability to manage performance, thermal stress, and power reserves under these extremes is literally what makes the aircraft safe to fly.
That's it. It's the ball game.
That sets up the problem perfectly. We have complex hardware, extreme dynamic demands, and this constant conflict between short-term efficiency and long-term asset health. You mentioned that traditional static rule-based controllers, use the ICE until SOC hits 50% and then charge. They just can't handle this. They hit an efficiency ceiling because they lack foresight. So what's the conceptual breakthrough of this EMS?
The breakthrough is moving from those static rules to a hierarchical dual-layer control architecture. We separate the decision-making by timescale. This ensures every instantaneous millisecond-level decision is always supporting a long-term, globally optimal strategy.
So you separate the strategic thinking from the quick reflexes.
A perfect way to put it.
Okay, let's start with the strategist. The deep thinking brain.
That is layer 1, the strategic layer, or the slow loop. This layer uses an algorithm called Model Predictive Control, or MPC. This algorithm acts as the global energy planner. It's the system's flight management system, but purely for energy.
How does MPC work in this context? What's it looking at?
It uses information from the flight management system, the FMS. So that's the actual flight path, predicted weather, any potential air traffic control hold points, and critically, the current battery state of health and its thermal state. It uses all that to predict the vehicle's energy needs, say 30 to 60 seconds or even several minutes into the future.
So it operates on a predicted time horizon.
Exactly. For instance, if the FMS shows a high-power climb transition is required in 45 seconds, the MPC knows the battery needs to be ready, both electrically and thermally. It's not just reacting to the pilot's current thrust request, it's looking down the road.
And what does this predictive planning actually generate? What's the output?
It solves for the globally optimal battery SOC reference trajectory. We call it SOCRE.
This OCRE.
It's a precise curve the battery's state of charge must follow throughout the entire mission to achieve the lowest overall cost, that's fuel plus battery degradation, while guaranteeing the necessary power reserves. It also pre-plans crucial thermal management commands, like preemptively cooling the battery 5 minutes before a known high-power event.
And this is all happening at a slow pace.
Very slow, it's strategic, it operates at a frequency of about 0.1 to 1 hertz. So once every second or two, it recalculates this optimal path.
Okay, that sets the goalpost. Now we move to the instantaneous action layer, the quick reflex nerve that actually executes the plan.
That's layer 2, the tactical layer, or the fast loop. This layer employs the adaptive equivalent consumption minimization strategy, or AECMS. This is the instantaneous power arbitrator. It operates at a dramatically high frequency, 100 hertz, a 10 millisecond loop time. And its job is critical. Take the pilot's immediate thrust command and, constrained by that strategic SOCRE from the MPC, minimize the instantaneous total equivalent fuel consumption.
That word equivalent is the key here. It's not just minimizing the fuel flow from the tank. It's weighing the fuel used against the battery power used. This is where the equation comes in. Help us break down the core mathematics of ECMS for the listener.
Absolutely. The system is always trying to minimize a cost function, which we call JFT. Conceptually, JFT is the total cost of operating the system right now in this millisecond.
Okay.
It has two main components. The first part is pretty simple. It's the mass flow rate of fuel, the literal fuel you are currently burning. The second part is the cost of using electrical power from the battery. We convert this electrical energy into an equivalent fuel mass by dividing it by the lower heating value of the fuel.
So the equation, which is basically J equals fuel burn plus some factor times battery power, it's saying minimize the total instantaneous energy cost where electricity is treated as if it were fuel.
Exactly. And the most critical, most complex element in that equation is the adaptive factor, which we call S of T. If this factor were just a static fixed number, the ECMS would be locally efficient but globally blind. It would just make the best decision for the next 10 milliseconds, regardless of the overall mission.
So the adaptive factor, S of T, this is the bridge that links the short-term instant decision layer 2 back to the long-term strategic plan from layer 1.
It's the secret sauce. It acts as an economic regulator for electricity use. We use a PID controller proportional integral derivative to dynamically adjust S of T. This controller constantly monitors the deviation between the current actual SOC of the battery and the MPC planned SOC's trajectory. This creates a powerful self-correcting feedback loop.
Let's talk about that feedback in a practical sense. How does S of T regulate the system's behavior?
Okay, so imagine the battery is currently at a higher state of charge than the MPC said it should be at this point in the flight. The system realizes it has a surplus of energy. The PID controller detects this positive deviation, and it decreases the value of S of T. A lower S of T means that, in that cost function, using electricity now appears cheaper relative to burning fuel.
So it incentivizes the system to use the battery.
Exactly. It encourages the ECMS to command the P3 motor to draw more power from the battery and rely less on the ICE. This helps to discharge the battery back down toward that optimal path, and it preserves fuel in the process.
That is smart. It actively encourages the system to burn off the surplus charge. And what if the battery is lagging, if its SOC is lower than the optimal trajectory?
Then the opposite happens. The PID controller detects that negative deviation and it increases S of T. A higher SFT makes electricity use look more expensive in the cost function. This forces the ECMS to command the system to rely more heavily on the ICE.
Either for propulsion or for charging.
Right, either by directly using the ICE for propulsion in parallel mode, or, if the power demand allows, running the ICE to charge the battery via P1. This mechanism guarantees that the short-term, locally greedy ECMS decisions are always steered toward meeting the global strategic association at the end of the mission.
Which ensures you have the required reserves for a safe landing.
Always.
So if the EMS were a financial manager, the NPC sets the long-term investment strategy, and the AECMS is the high-frequency trader whose prices are constantly adjusted by the PID controller to meet the long-term portfolio goals.
Yeah,
That makes the conceptual link much clearer.
that's a great analogy.
Now that we understand the strategic and tactical layers, let's say how this intelligence translates into physical action. All of this is executed via the mode management state machine, which dictates how the 3 motors, 2 energy sources, and that key-0 clutch all interact.
Yes, the EMS has to flawlessly transition between 4 core energy flow states, and it often has to shift from one to the next in a fraction of a second, balancing efficiency, raw power, and acoustic requirements.
Let's start with ground operations, or flying over sensitive areas.
That's the E-taxi hover mode, or EV mode. This is designed for ground taxiing, holding patterns at an airport, or hovering over a sensitive location like a hospital helipad. In this mode, the K0 clutch is open, the ICE is off or idling, and all propulsion is driven purely by the battery.
And the objective is critical for commercial adoption. 0 emissions and low noise in those terminal or residential zones.
Precisely.
Okay, next, the absolute demand for power. Takeoff.
That requires parallel boost. This is the peak performance mode. You need it for moments like vertical takeoff, initial climb out, or a critical go-round maneuver where you need every bit of available power instantly.
So the K0 clutch snaps closed.
Snaps closed, mechanically linking the ICE to the driveline. The EMS commands the ICE, P1 acting as a motor, and P3 to all simultaneously output maximum torque. It integrates every available watt and horsepower for that transient peak thrust.
And series charging when the system needs to replenish the battery.
Right. Series charging is used when the SOC dips too low or when the MPC strategically plans to restore charge ahead of a critical maneuver. The K0 clutch is opened, intentionally decoupling the engine from the rotor.
So the engine is just a generator now.
The ICE drives P1, which acts as a powerful generator. The electricity produced powers P3 for continued flight and sends any excess energy back to the battery. And the critical objective here is to run the ICE at its ideal operating line, its IOL, which is its most efficient point, even if the flight's power demand is low. We prioritize running the engine where it's happiest to maximize generation efficiency.
That is smart. But let's talk about what seems like the most technically clever mode for efficiency during flight.
That would be the load point shifting cruise, or LPS mode. In this mode, K0 is closed, so the ICE and P3 are both providing drive torque. But here is the counterintuitive stroke of genius.
Okay.
The EMS mandates the P1 unit to generate power, even though the engine is already driving the propulsors.
Wait, hang on. If the ICE is already providing cruise power, why would you actively force P1 to generate electricity? That generation imposes an artificial load on the ICE, and then you immediately lose some of that energy through electrical conversion losses. Why make the system work harder only to lose power?
This is a perfect illustration of system-level optimization overriding component-level efficiency. The problem lies in the ICE's innate inefficiency at low power settings.
Okay.
For a typical cruise flight, the total power demand might only require the ICE to operate at, say, 30% of its maximum torque. At that low load, the engine is running very inefficiently. Its brake-specific fuel consumption, or BSFC, which is basically the engine's miles per gallon, might be terrible, maybe over 350 grams of fuel per kilowatt hour.
Right, so the EMS recognizes this.
It recognizes this localized inefficiency. By forcing P1 to generate power, it artificially increases the total torque load on the ICE, pushing its operating point up to, say, 60 or 70% load. This higher load point is the engine's sweet spot, where the BSFC dramatically improves, often dropping below 240 kWh.
So you take a small electrical conversion loss at P1, but you get a massive efficiency gain from the ICE itself.
Precisely. The immense fuel savings gained from moving the engine into its most efficient operating zone far, far outweigh the minor electrical losses from P1 acting as a generator. And that generated electricity isn't wasted. It's stored back in the battery for the next time you need a boost.
So it's actively making the engine work harder to make the overall system run smarter.
That's it.
That speaks volumes about the intelligence of that MPC layer. Let's expand on that predictive capability. How does the MPC translate prediction into preemptive safety?
Through what we call predictive energy planning. The MPC is always consulting the FMS flight profile. Let's go back to the landing example. A vertical landing is a critical high-power maneuver.
Right.
If the MPC sees that the aircraft will start its final approach in 5 minutes, it doesn't wait for the SOC to hit some hard minimum threshold. It proactively initiates a targeted charging phase. Maybe it switches to series charging or commands load point shifting to ensure the battery is charged to a required safety level.
Guaranteeing 100% stated power availability for that maneuver.
Exactly. This foresight prevents that catastrophic scenario where the pilot calls for full thrust during an emergency go-around and the battery is thermally or electrically unable to respond. Safety is achieved through pre-planning.
That addresses the strategic flow. But what about the milliseconds of difference in physical response? We noted that the ICE is slow and the electric motors are almost instant. How does the EMS manage that mechanical constraint?
That's handled by dynamic torque response matching, which we often just call torque fill. The physics constraint is stark. The ICE has inertia and fuel flow latency, right? This typically results in a lag of about 200 milliseconds to deliver commanded torque.
Which feels like an eternity in flight.
It is. The electric motors P1 and P3 are instantaneous. They respond in about 10 milliseconds.
So if the pilot punches the thrust lever, and that full command goes straight to the slow-to-respond ICE, the pilot experiences a dangerous thrust delay, which would be especially critical in low-altitude maneuvering.
That's one problem. The other is mechanical stress. Sending a high-frequency sudden torque demand directly to the transmission would cause severe shock loads and rapid mechanical wear. So the EMS tackles this with a highly orchestrated dance.
How does that work?
When a rapid acceleration command is issued, P1 and P3 immediately deliver the high-frequency torque needed to fill that 200 millisecond ICE delay. This ensures the pilot experiences smooth, instantaneous thrust.
And what about the ICE?
Simultaneously, the EMS applies a sophisticated rate limiter to the torque command being sent specifically to the ICE. This forces the mechanical components to spool up safely and smoothly. The electric motors basically absorb all the transient high-frequency demands. They act as a highly sophisticated electronic shock absorber, protecting the transmission while maintaining the pilot's perceived instantaneous control.
That is the ultimate marriage of mechanical robustness and electrical responsiveness. Okay, finally, a less glamorous but vital piece of operational intelligence, managing the K0 clutch.
Right, the K0 clutch switching penalty. Every single engagement and disengagement of that clutch causes mechanical friction, wear, and thermal stress.
So while switching modes, say, from series to parallel, can provide an immediate fuel efficiency gain, doing it too often would lead to clutch chattering, severe mechanical wear, and prohibitively high maintenance costs.
Exactly. So the EMS needs to prevent the AECMS from being too greedy about short-term efficiency if it means the components wear out too fast.
How does it do that?
The EMS logic incorporates the estimated mechanical wear cost of a K0 engagement directly into the AECMS cost calculation. The solver now has to balance the immediate fuel savings against the amortized long-term cost of component durability. This prevents the system from making overly high-frequency, short-sighted switching decisions, ensuring that operational efficiency serves the greater goal of long-term commercial viability.
So it's even factoring in future maintenance bills into its real-time decisions.
It has to. That's paramount for the certification and operational life of the whole system.
Okay, we've established the EMS is incredibly smart and efficient, but now we hit the aviation wall. Safety. In certified air transport, intelligence is secondary to deterministic reliability. The EMS manages power delivery for flight control, so any error can be catastrophic. The regulatory benchmark set by EASA and the FAA is a probability of catastrophic failure of less than 10 to the -9 per flight hour.
One failure in a billion hours.
Which is an almost impossible standard.
This is where advanced control systems meet their greatest regulatory challenge. Smart optimization algorithms like MPC, they're inherently non-deterministic. Their output relies on predicted states, models, real-time sensor data. That means we can't possibly test every single outcome. And regulators, they demand determinism and verifiable proof of safety.
So how do you certify a flexible predictive algorithm to that impossible $10 standard?
We do it through layered defense and architectural separation. We adopt our first protection strategy, hybrid certification, which uses a mixed-DAL strategy. DAL is design assurance level, aviation's measure of software rigor. DALA is for functions whose failure is catastrophic. DALC is lower for functions whose failure is major but not catastrophic.
Walk us through that separation. How does it work?
We logically partition the EMS software into two independent channels running on separate hardware or execution cores. First, you have the optimization channel, which we certify to DALC. This contains the complex, non-deterministic MPC and AECMS algorithms.
So you assign it a lower assurance level.
Exactly, which significantly reduces the cost and time of certifying that complex probabilistic code.
So the smart, flexible, difficult to certify part is sequestered. How is safety guaranteed then?
By the second channel, the monitoring channel, certified to DLLA. This layer is simple, deterministic, and ruthlessly independent. It contains only basic, rigorously tested arithmetic rules. Its only job is to check if the output of the DLC optimization channel remains within a predefined, static, and safe flight envelope.
So it's a safety guardrail.
It's a guardrail. It checks if the commanded torque exceeds structural limits or if the SOC drops below the emergency reserve. This strategy isolates the complexity while maintaining the absolute highest safety assurance on the final output.
So the complex algorithm is allowed to be clever, but it's constantly supervised by a simple, non-negotiable safety system. But what if the DLLC channel generates a command that is grossly erroneous, say, due to a sensor error that doesn't violate the envelope but still deviates wildly from what the pilot intended?
That leads to protection strategy, too. The independent safety limiter, also DLLA, this is the ultimate non-negotiable line of defense specifically against loss of thrust control, LOTC, or unintended thrust increase UITA. It absolutely must be guaranteed to work under all fault conditions.
And how does the limiter work in real time?
It employs a very simple deterministic logic. It constantly compares two signals, the pilot's original thrust command and the final optimized total torque command coming from the EMS optimization layer.
Okay.
If the deviation between those two exceeds a preset tight threshold, we often use 10%, and that deviation persists for a specified duration, say 500 milliseconds, the limiter instantly activates.
Why the duration? Why not activate it instantly?
We have to avoid nuisance trips. Small, instantaneous deviations are normal during transient operations. But a 10% deviation persisting for half a second indicates a fundamental software error or a severe sensor failure has corrupted the optimization output. When that happens, the limiter immediately bypasses the entire optimization algorithm.
And what does it switch to?
It switches to a simple, fixed, and rigorously pre-verified thrust allocation ratio. This ratio is guaranteed to maintain safe, if suboptimal, flight control. And because the limiter's logic is so simple, so transparent and isolated, it can be certified to DALA. It provides an absolute guaranteed safety floor beneath all the complex intelligence.
That addresses external errors. What about internal faults? The algorithm simply failing to run.
That's protection strategy 3, algorithm health monitoring. Real-time optimization solvers, particularly MPC, are computationally intensive. Under extreme data loads or unanticipated conditions, the solver might fail to converge to a solution, or it might simply exceed the time allotted for its calculation.
And timing is everything in a 10-millisecond control loop.
Absolutely. So we install an independent watchdog mechanism that monitors the solver's execution time. That 100 Hertz loop runs every 10 milliseconds, but we mandate a strict worst-case execution time limit, a WCET of 8 milliseconds or less.
Leaving a 2-millisecond buffer for system overhead.
Right. If the solver fails to converge, or if its WCET exceeds that 8 meters hard limit, the system automatically and seamlessly switches to a conservative, fully validated, rule-based backup control strategy.
So the system defaults to dumb but safe, rather than smart and slow.
Precisely. Deterministic timing and safety always trump advanced optimization in aerospace. And when this event occurs, a non-critical advisory alert, EMS degraded, is sent to the cockpit, confirming that the advanced intelligence is offline, but the core safety of flight is maintained by that pre-validated backup logic.
This multi-layered, segregated, time-assured architecture. It sounds like the only way you could introduce this kind of advanced, non-deterministic control into the 10-knotter airworthiness environment.
It's the only way.
Okay, safety requires proof. And in aerospace, that proof is codified by the V-model development process, which adheres to standards like ARP 4754A. You move from abstract requirements down the left side of the V and then climb the right side, verifying those requirements against physical reality. We need to see how the EMS moves from a concept on a whiteboard to a certifiable component on the aircraft.
The V model guarantees traceability. Our validation process moves through three critical escalating stages of fidelity.
And stage one is purely computational, the simulation world.
That is stage one, model in the loop, or MEL simulation. We start with a highly comprehensive digital twin built in environments like MATLAB Simulink. This model includes high-fidelity mathematical representations of the aerodynamics, the full powertrain dynamics, the battery electrochemistry, thermal models, everything.
Well, the EMS algorithms are validated here against thousands of simulated flight profiles.
Every known edge case, extreme temperatures, sudden component degradation, you name it.
What are the key performance indicators you're verifying at this stage?
We're verifying the core algorithmic correctness and the efficiency targets. The critical goals are proving fuel savings of at least 5% compared to non-optimized strategies, and ensuring the mission and SoC control precision is tight, meaning the final SoC is within 2% of the MPC's target value. If the algorithm can't meet its targets in simulation, there's no point moving to hardware.
Stage two takes the verified software and introduces the actual brain hardware.
That is stage two. Processor in the loop, or PIL testing. We take the verified algorithms, auto-generate them into certified C code, and we deploy that code onto the actual target flight computer, something like the NXP S32G3 vehicle network processor. The simulator still runs the physics model, but the actual flight-ready chip is running the control logic.
And what's the primary objective of PIL testing?
Timing assurance. This is where we verify that the code, when executed on the constrained flight processor, can meet its real-time requirements. We measure the worst-case execution time, the WCET, under load to rigorously prove that the MPC and AECMS single iteration time remains reliably under that critical 8-millisecond threshold. If the code is logically correct but too slow, it fails PIL and has to be reoptimized.
And the final, highest fidelity test before risking an actual flight test.
Stage 3, the Ironbird integration test. This is a full-scale, one-to-one physical test bench. It integrates every physical component, the real ICE, the real P1 and P3 motors, the actual K0 clutch, and the high-voltage 800V battery pack, all wired together as they would be in the aircraft. This is where we verify the interaction between the software intelligence and the mechanical reality under real power.
The ultimate stress test. What is the focus of the Ironbird phase?
Comprehensive fault injection testing. We intentionally try to break the system. We simulate catastrophic sensor failures, for example, injecting sudden, unrealistically large jumps in the SoC sensor signal. We simulate pilot command signal loss or artificially generate unexpected ICE response lags.
And you have to verify that in every single fault scenario.
The deterministic safety limiter and the rule-based backup control strategy successfully activate and maintain safe flight control authority. We also perform tens of thousands of K0 mode switching cycles under load to verify the component durability against the software management strategies.
This rigorous V-model process culminates in a set of key performance indicators, KPIs, and acceptance criteria that are non-negotiable for final airworthiness acceptance. These are the go-no-go conditions.
Right, and we organize these KPIs around the three pillars of success: safety, efficiency, and control quality.
Let's start with safety.
For safety, the regulatory mandate stands. Catastrophic failure probability has to be below 10 to 9 per flight hour. Critically, we have to demonstrate zero occurrence of loss of thrust control or unintended thrust increase in any sensor fault scenario we inject. The safety system must prove infallible.
And what about thermal safety with the batteries?
Given the high-density battery packs, thermal management is a huge safety KPI. Post a single-cell thermal runaway event, the containment system must prevent heat and fire spread for a minimum of 15 minutes. That 15-minute window is a regulatory standard. It's designed to ensure sufficient time for the aircraft to execute an emergency landing and for passengers to safely evacuate before thermal propagation compromises the cabin.
And no toxic gas leakage into the cabin.
Zero toxic gas leakage. That is a hard requirement.
Those are demanding. What about the commercial viability pillar efficiency?
For efficiency, the results must quantitatively validate the superiority of the hybrid architecture. We require the cruise fuel economy improvement to be greater than 25% compared to a traditional, passively controlled ICE vehicle. And crucially for range anxiety, the operational range must be increased by more than 2 times compared to a pure EV variant using the same battery footprint.
If you can't deliver that range multiplier, the whole hybrid approach fails its commercial mandate.
It fails. Simple as that.
And finally, the passenger experience and component lifespan control quality.
Control quality is measured rigorously. For passenger comfort during mode transitions, the rotational speed ripple, that momentary fluctuation you might feel during a shift, it must be less than plus or minus 2% when the K0 clutch engages or disengages. The K0 clutch engagement transition itself has to be extremely fast, less than 200 milliseconds, to ensure continuous, smooth thrust delivery. And finally, we mandate a crucial safety assurance. The system must automatically and permanently lock in a minimum 20% SOC as an emergency reserve. This reserve is explicitly dedicated for a potential missed approach, an immediate landing, or a go-around maneuver. It cannot be depleted for mission efficiency purposes.
This deep dive into the P13 EMS engineering specification, it really reveals that the system isn't merely solving a power problem, it's solving an integration and certification paradox. It successfully merges that high efficiency with the absolute deterministic safety required for certified aviation.
The EMS is, and this isn't hyperbole, the key technical foundation for achieving commercial success in advanced air mobility. Its achievement rests on two core pillars. The first is superior performance efficiency, which is achieved through that dual-layer optimization. The MPC's global foresight combined with the AECMS's instantaneous, economically informed power arbitrage.
Right, which allows the aircraft to do things like load point shifting to extract maximum value from every ounce of fuel and every joule of battery energy.
Exactly. And the second pillar, which makes the whole thing flyable in a regulatory sense, is absolute safety and certifiability.
Which is addressed head-on by the sophisticated deterministic architecture.
The DAL, a safety limiter, the robust mixed-DAL strategy, the constant algorithm health monitoring. We've essentially constructed a defined, certifiable safety perimeter around advanced probabilistic control algorithms. We're systematically addressing the core regulatory hurdles facing intelligent, flexible systems in aviation. This system is the critical step from traditional static automation to higher-level intelligent control in aerospace.
So what does this all mean for the future of flight and for the engineers designing the next generation?
Well, the strategic implication is clear. Companies that master the science and strategy of energy management, that can integrate aerodynamics, battery physics, thermodynamics, and commercial operations into one cohesive, predictive control system, they are defining the future shape of aerospace. The EMS represents a massive engineering coordination effort.
It's the brain that has to speak every language.
It does. And here's a final provocative thought for you to consider as you think about how this complex system operates. We detailed how the EMS successfully solves the counterintuitive trade-off of forcing the engine to generate power to save fuel. That was the challenge for P13. So what is the next counterintuitive trade-off that intelligent control will solve for future electric aviation? Maybe it's something about the relationship between maximizing charging speed on the ground and minimizing long-term battery cycle degradation. And more importantly, how will we certify that next level of intelligence when full autonomy, which depends entirely on probabilistic algorithms, is the industry's ultimate goal? That complexity and that certification challenge is what the next generation of architects is already facing.